Vatsala?
Yes, Anjali, we are
okay.
live on YouTube.
Yes.
Yeah, go ahead.
Where do I see the link to post? I'm just trying. I mean, for the
Yes.
YouTube, should I put the same link? Or?
Go on top. There is live on YouTube on Zoom. Do you see it?
Okay, go ahead.
Actually, can you hear me?
You can go to the ACI website.
Okay, okay.
Okay, let me do a screen share.
Yeah.
One second. We have 2 more minutes. Should we start or should we wait for 2 minutes?
A couple more minutes. We have like around 20 people. Maybe just wait for a couple of minutes.
Okay.
Start in 2 minutes, yeah.
Sure.
Do I need to put the YouTube link for ACI events official WhatsApp?
Yeah, go ahead.
Okay.
I'm going to start now because otherwise we'll be late for, just give me 1 second.
The 3 people in the waiting room, I'll take care of them.
Okay, great. Thank you. So let's start. Hello, everyone. We at ASEI hope that you're doing very well and staying safe. Socrates had once said that man must rise above the earth to the top of the atmosphere and beyond, for only thus will we fully understand the world which we live in. And today we have Dr. Ranga Chary to take us through the journey of cosmology, which is, in a way, the oldest and the youngest of sciences. But before we set forth in that journey, let me remind you of a few earthly things, namely a few housekeeping tips. The session is being recorded and it is also live on our YouTube channel. We welcome you to revisit the content as it will be available on the channel and also share it with your friends. While you are there, you might as well go ahead and subscribe to our YouTube channel. That way you will get our updates on a very regular basis. While the session is on, we request you to mute yourself and keep your videos off so that we can listen to the speaker without any interruption. In the meantime, feel free to put your comments and questions in the chat. We will be monitoring the chat and taking your questions to Dr. Chary. Dr. Chary too wants a session to be very interactive, and time and again he would be asking you some questions. Please reply to it in the chat itself. Following the presentation, we will be engaging with the audience in a networking session. So be with us till the very end, please. Let me now hand over to Muthu, our Michigan chapter president, with 25 years of industry experience, ranging from product management, R&D, market intelligence to consulting. He's passionate about renewable energy's significance in combating the climate change, unlike some of us. I will have Muthu say the rest of it himself and start the journey today. Over to you, Muthu.
Thank you. Can you guys see my screen?
Yes.
Perfect.
Yes.
Great. Thank you once again. Good morning, California. I know it's very early. Thanks for joining on your Saturday morning. For the Michigan friends and people east of us, good afternoon and good evening. Who's really curious about cosmology? I'm sure I am, and which I have no idea about. So before we deep dive and take the journey with Dr. Chary, couple of introduction from the chapter. Basically, warm welcome from ASEI, from the national chapter, from the Michigan, as well as SoCal chapters. We warmly welcome you. And ASEI, as an organization, is 39 years old. We started right here in Michigan. And next year, we are marking our 40th anniversary. We started as mainly as a platform to network technology professionals and to help them as well as to do with career advancement, community development, also stay as a means to do technology exchange. And that is our main vision, with a very specific purpose of grooming tomorrow's engineers and technology professionals, and through YTE and some of the programs. So kids are our future, right? And we do that through some of these initiatives. The last couple of years, we've been embarking on Mentor Connect, University Connect, YTE, that stands for Youth Technology Exposition, and consistently delivering engineering tales, kind of technology exchange series. And this year, we also started a new Corporate Connect. And before get on to what's coming up this year, a quick recap on 2021. We all, we were locked down. We went through the pandemic, but 2021 we still were, connecting with our members. So we hosted people like bureaucrats. Or Chicago's Consul General was here, and he graced us with a speech on technology. How U.S.-India relations can, how U.S. is investing in India and vice versa. Then, as a tradition, in March, we celebrate Women's History Month. And last year, definitely, we had a great set of panel of women talking about social entrepreneurship. Then we launched our, along with the huge, planning and effort by our national team, we partnered with the national team in promoting our AI Summit 2021, where we are technology leaders all the way from Silicon Valley to Midwest, talked about AI and jobs and etc. Middle of the year, Dr. Bansal took us on his flight, throughout his solo flight around the world, and shared his insights and experience, how he did that for a purpose. Later, he went on to finding interesting oxygen concentrator companies and so on. And we also connected in the grassroots level locally by partnering and being a voice of engineers at the various local, social, and political forums, as shown here. In 2022, we really are itching to put the pandemic behind us, and we have an interesting lineup of events coming up. Not to forget, even tomorrow, marking our 34th National Convention, we just concluded like a month back. Around that event, we honor achievers and long-time awardees. So there's a special program planned by our national team. Join and take benefit. And it'll be chaired by the chief guest of tomorrow's program is Ambassador of India to US, Sandhuji. Please take benefit. And our flagship Mentor Connect program returns in 2022. This time we want to double the number of mentees. So last year we had an excellent opportunity to do one-on-one career guidance for senior technology executives to entry-level engineers. Hey, I was a beneficiary, and I benefited from that. I was a mentee last year, and I benefited a great lot from this. This is happening exactly next week, March 5th, at the same time. So one other benefit of value to our members. And ACI Michigan, like many other chapters, are itching to come in person, right? So celebrating our Women's History Month, we are planning to do an in-person event right here in Michigan. Ashwini Balasubramaniam would be our guest speaker, and she's diversity expert, women's empowerment, sustainability expert. She sits on various automotive women's alliance, so she'll grace the speech, and the topic is going to be empowered women, the key to a sustainable future. One of our board members here, Vatsala, who also is a president of My Family Services, she'll be co-chairing and talking to Ashwini on this program. And what's ASCI without YTE, right? STEM is our DNA. So we continue this year too by partnering with the local science fair, where we encourage, promote, and learn from their projects. The kids put out phenomenal array of projects they embark on. And these kids go on to the National Science Fair, but we consistently support and mentor as well as learn from these kids. And drum roll, in-person event returning to Michigan would be our national convention this year. We just announced that in the national our last month program too. Fall of 2022, we'll have one right here in Michigan. Talk about collaboration. This our ACI Washington DC chapter volunteered, and they would be co-hosting the event with us. They will do this jointly, and stay tuned for more details. And hey, it's Michigan. So the topic is going to be sustainable transportation and infrastructure. It's a summit on sustainable transportation and infrastructure. More details to come soon. And again, talking about collaboration, right? This event today with Dr. Chary, where he comes from SoCal. So our SoCal chapter partnered with us in putting this fine program. So let me hand over the mic to Sri Gavini for saying a few words.
Thank you, Muthu. Good morning, everybody. Thank you so much for being here today. And I really want to thank Dr. Chary, Ranga Chary, for being here. And I'm really looking forward to the talk. And I think I shared it everywhere I could. And a lot of my friends kept saying, all right, you shared it enough, we'll try to join it. So, but I'm part of the ACA SoCal team, and I'm Sri Gavini. I work as a business development manager for a private organization called Valen. And this is our 2021 and 2022 board, and we are trying to add a few more people. And this is a young board. We started in 2021, and we have a lot of events coming up in this year as well. Stay tuned for it. And we really appreciate this opportunity and looking forward for many more collaborations to come forth. Thank you.
Thank you, Sri. And we are here. Before that, I just want to leave you guys with one word. As soon as I heard about Dr. Chary, one thing came to my mind and quite prevalent, as they say in Tamil, by this sage and 4th century Tamil poet, Katrathu kaiman alavu, kalladadu ulagalavu. What that says is what we have learned so far is a mere handful. What we haven't learned is much bigger than this world. This party grandma said this, many centuries ago. That's when I realized, hey, there is a huge difference between world, planet, universe, and universes. And not just me. When you Google this saying, NASA comes up. Even they chose to inscribe this famous quote in their museums. So, without much further ado, let me invite our own chapter director here, Kush Shah, to moderate the rest of the session and introduce our, Dr. Chary.
Good morning. Thanks, Mayamato. Good morning to the West Coast. Good afternoon to the East Coast and Michigan. It is my honor to introduce Dr. Ranga, who is a senior researcher and project manager at the U.S. Planck Data Center at Caltech. It is on the science headlines lately. His broad interest includes understanding how nature works, either on the sky or on the land or under the water. His research spans from a number of topics, from the origin of the evolution of the universe to the formation of early galaxies and characteristics of planets outside the solar system. Dr. Ranga holds a PhD in astronomy and astrophysics from UCLA and is a CS alum from NIT Trichy, India. His recreational interests include scuba diving, wildlife conservation, and exploring places which are off the beaten track. In addition to being a genius, he is a very humble person. So it is a great pleasure to introduce him. As Vatsala has mentioned, please type in your questions into the chat box and we'll be monitoring it. So let's give a welcome to Dr. Ranga. Thank you for taking the time from your busy schedule. Thank you.
Thanks very much for having me, everyone. It's nice to be here. I'm going to share my slide in a second. So what I'm going to report to you today is on the search for alternate universes. We've clearly heard this term many times in the news in the last several years, but this is the scientific viewpoint. This is not what you hear typically about people living in alternate universes. This is not what this is about, because that is not a scientific viewpoint. Here we're talking about, are there other universes out there with different physical properties than our own, and why they may exist, and how we get to studying about these alternate universes. So for those who don't want to listen to the whole talk, the short answer is we have not found one yet. And the scientists have a very high bar for believing that something is real. And typically this is classified as the false probability, false signature probability. And so something has to be 5 times above the statistical noise, which gives it a probability of 1 in 100 million for it to be an unlikely event, for it to be a definitive thing. So, we have a very high bar for claiming that something is real. And so we see evidence for anomalies, and I'm going to talk to you a little bit about what these anomalies are. All this research that I'm going to present is actually based on this mission called Planck, which you can see on the top left. And this is a European Space Agency mission, which was launched in 2009. We took data for 2013. And we have spent the last several years just analyzing the data that comes from this mission. So let's think about what the worldview was back in 350 BC. And this is what the people thought the entire planet looked like. It was basically the Mediterranean, the countries around it. They didn't know about the Americas. They knew about India, but not really about Australia and Oceania. So it was a very limited worldview back in 350 BC. And of course, through the spirit of exploration, which was funded by various European kings, rulers basically, they went off to the edge of the world, so to speak, with the fear that they may fall over, but they still ventured forth, and they ended up with a map of the universe, which is much like this, which is the worldview of the universe in the 17th century. And now you're starting to see all the different continents, maybe not all of them in the South Pacific, but we're making good progress. We have a good map of India here, getting the coastline of Australia. So over those 1700 years or 2000 years, we have made, by taking measurements, we have made progress in understanding what our planet looks like. But cosmology is the study of things beyond our planet. It is about understanding the universe in which we live. And that itself has changed. I mean, now we have light pollution in all the major cities. And so it's very hard to see the 6,000 odd stars that you can see with the naked eye. But if you go to a really dark spot, like, well away from the cities, like in the middle of the desert or places in South Central Africa, where there is no light pollution, you will actually get an amazing view of the night sky. And 3,000 years ago, when people looked at the spectacular night sky of 6,000 stars, they noticed that there was a band of gas and there was a band across the sky, which was actually our Milky Way, our galaxy in which we live. And this band is because of the gas and dust which is inside our galaxy. But what they interpreted this 3,000 years ago is there was the goddess Nut, who basically spanned across the entire sky. And the stars and planets move across it, and you basically rise up this way and you set this way. And so that was the worldview of how the planets and the stars on the sky move in the course of a day, over several days. Now, after taking a lot of measurements mostly in the last 50 years, last 60 years, we have built on this knowledge. We know that what I show here is the state of our universe. On the left is the beginning of the universe, which is started with something like the Big Bang. And what on the right is our planet, which is around the sun, orbiting around the sun. So on the right, let's start with this easy stuff first. Let's start with the solar system. So we live on a planet Earth, which you saw a good map of, which is orbiting the sun. There are other planets out there. There is this gas and dust, which is the zodiacal dust, which is also in the plane of our galaxy. Our sun is a fairly ordinary star. It's one of 100 billion stars, which is way out in the outskirts of a galaxy called the Milky Way. And so it's about 25,000 light years away from the center of our galaxy. So it's not even anywhere in the dense central regions. And the band you see across the sky when you're in a really dark spot is the plane of our galaxy. Because as you can see, all this, you can see the bright spots are all stars, the dark spots are all gas and dust. And so that band that you see across the sky is the gas and dust obscuring the starlight that gets to us. But our galaxy, which has 100 billion stars, is not the only one out there. We are part of a local group of galaxies, but there are about 1 million billion galaxies out there in the universe, a good fraction of which have been mapped, but not all of them have been mapped. And then once these clusters of galaxies are located along filaments and clumps in the underlying distribution of matter in the universe. And so we are here, 13.8 billion years after the Big Bang. And if you go back in time, we have found galaxies all the way up to about 200 million years after the Big Bang. So we made a lot of progress. And studying this area, which is labeled as the dark ages, is one of the current frontiers of astrophysics, which we're making progress on with the new telescope launch called the James Webb Space Telescope. Looking even further, we have something called this era of recombination, and that's basically an epoch in which we can see the Big Bang radiation. So we have detected radiation up to here, but we can't see galaxies much beyond here. And by studying the properties of this radiation, we can understand everything that happened back since between the Big Bang and 380,000 years after the Big Bang. We know that the universe underwent a very rapid period of expansion called cosmic inflation in the first microsecond after the Big Bang. And then ordinary matter formed out of a soup of particles and antiparticles and photons. And gradually the universe expanded and cooled. And then we detect this Big Bang radiation, which is a result of all these processes happening out here. And all the matter, all our galaxy, our planet, our star, everything that we see basically formed out of this quark gluon plasma, which existed back in the first fraction of a second after the Big Bang. So that's, all these are measurements. I can show you a measurement which proves much of this. The thing which breaks down is whether there is something like the Big Bang. Because at the Big Bang, the physical processes actually break down, the equations break down. And so it's very hard to explain whether there was actually a singularity right at time t equals 0. It's possible that there was, but there's some school of thought that maybe it was a cyclical universe. The universe keeps expanding and contracting, expanding and contracting. So I hope this gives you a flavor of where we are in the universe. I mean, we're a fairly ordinary planet around a fairly ordinary star, inside a fairly ordinary galaxy, inside a fairly ordinary cluster of galaxies, in a universe which has been around for 13.8 billion with a B, years. Okay. So the problem is to get the parameters of our universe as they are, to get a universe which lasts for at least 13.8 billion years, which has the amount of matter that we have, to have the amount of vacuum energy that we have. The density of the universe has to be fine-tuned in these initial conditions to 1 part in 5 times 10 to the 24. Now that's a staggering number. I mean, if you think about us humans, each human is unique and has had unique experiences. Basically 1 in 7 billion, you're 1 in 7 billion people on the planet. So you have had unique experiences, and the probability of somebody else having an identical set of experiences is at least as small as that, if not even smaller. So 1 part in 5 times 10 to the 24 is a really, really probabilistic number. And so the way to explain this is if the universe was slightly more dense than what we have right now, it would have collapsed on itself. And if the universe was slightly less dense than what we have now, it would have expanded forever and become a cold, dark place in which planets and stars wouldn't have even formed. And that's what is shown here, where on the y-axis we have the scale factor, and the x-axis we have time. The scale factor basically means at 1 is where we are, a equals 1 is where we are. And as I said, we are at 13.8 billion years on the x-axis. The black line shows the expansion of our universe based on all the parameters we've measured. The red line shows what would happen if the universe was slightly more dense by 1 part in 5 times 10 to the 24. And the green line shows what would happen if the universe was slightly less dense by 5 part in 10 to the 24. So if you want to know the actual numbers, here they are in grams per cc, which not a unit that astronomers typically use, but just here for illustrative purposes. So that begs the question, if the probability of having something unique is 1 part in 5 times 10 to the 24, are there multiple other things out there which may or may not have conditions which are suitable for the formation of life, or for the formation of stars, or for the formation of planets? And that's the big question. Are there multiple bubbles out there? Are there alternate universes out there? The remaining 5 times 10 to the 24 minus 1 or whatever the number is, 10 to the 500 minus 1, universes just don't have conditions suitable for the formation of life and our presence in them. And this is why you have all these little bubbles, like bubbles in a soda bottle. Each one has no galaxy or stars, while here we have our universe, which has the suite of galaxies and stars in them, and therefore has conditions which are suitable for life to form. So that's the big question. Now, this is a matter of big debate. There is a school of thought that searching for alternate universes is not a scientific endeavor because it's an untestable theory. And there is a school of thought that thinks, well, if it's a scientific theory, and it is, people have published many papers about it, then we should look for it, we should test it. And that's the beauty of astronomy. You have to take a measurement to prove whether something is real or not. And so that brings us to the Planck Mission, which is the abbreviated. So any questions until now? No? Okay.
Very good. Very good.
Yeah, there's nothing in the chat box.
Yeah,
keep
I
going.
think people are engrossed in your presentation, Dr. Chary.
So that brings us to, thanks. That brings us to the mission from which the data was taken, which is Planck. It was first proposed in 1993 with an expected launch in 2003. It finally launched in 2009, which is a minor miracle because typically each of these missions are unique and the complexity is so immense, you have invariable launch slips. And so this is a European Space Agency mission with NASA involvement. It consisted of 2 instruments, which worked in the radio frequencies, basically 9 frequency bands, unimaginatively named the low frequency imager and the high frequency imager. So the low frequency was between 30 and 70 gigahertz. The high frequency was between 100 and 857 gigahertz. The low frequency instrument was led out of Italy. The high frequency instrument was led out of France. And it was the high frequency instrument. It was the coldest instrument in space. It was at a temperature of 100 millikelvin because that's the temperature you need to beat down the noise of the detectors, which used the multi-stage helium cooling system to get the kind of sensitivity that we need. It was launched, as I said, in May 2009, in this, as you can see in this image, from an Ariane 5 from Kourou, French Guiana, to the Earth-Sun Lagrange point, the second Lagrange point, which is 1.5 million kilometers away from the sun. So it was not in orbit around the Earth because the Earth is too warm. And if you have something which is 100 millikelvin orbiting around the Earth, you basically need a lot of refrigerant, in this case, helium. And helium is very expensive. So we have to push it all the way out to 1.5 million kilometers away from the Earth. The cryogen, the helium, ran out in January 2012, and the end of operations happened in 2013. And this is what the satellite looked like. And every single component in the satellite is absolutely essential for taking the kind of data that we want. So how did Planck map out the entire sky? There we go. Let's see if this works. So it spins at 1 RPM. These things out here are basically to keep the satellite cold because it's facing away from the sun. The rays of light come in like this and hit the instruments which are here. And so by every 6 months, the satellite maps out the entire sky. So over the course of a year, it maps out the sky twice. Over multiple years, it maps out the sky, n times 2. And what you see here is a map of the entire sky. And that horizontal line that you see going right around the middle is the same plane of the Milky Way, our galaxy. So this is what you would see if you were in a really dark spot, in Africa or out in the desert or someplace. So this is how Planck mapped out the entire sky. And so these 9 frequency bands are shown here. This is what the map of the sky looks like. You can see qualitatively, they look about the same. In all cases, the center, the plane, you see this line going through the center, and that is the plane of our Milky Way. But what you see at high latitude, outside the plane of our galaxy, is the Big Bang radiation. In these cases, it becomes all the dust which is in our galaxy. There's a lot of dust, a lot of gas in our galaxy. So the reason you need all these different frequencies is so you can separate the different components of emission. It's much like peeling an onion. You take out layers one by one. And so by having all these different frequencies, you basically peel out each component of emission, which is in our galaxy. And as I explained to you, we're in a solar system, which has dust. The sun is in our galaxy, which has dust. And so you have to peel out, and our galaxy has cosmic rays, which produces more radio emission. So basically, that if we, by virtue of being somewhere close to the Earth, you always have all these sources of radiation. And so as the old saying goes, one person's signal is another person's noise. Basically, that's what it is. So some people who want to study the plane of our galaxy, well, that's great. You're getting all this radiation for free, which you can use to study the plane of our galaxy. But if you really want to study what the Big Bang radiation is, well, you need to peel out all these layers of the onion and then see what you can see outside the plane of our galaxy. So just to clarify this, does anybody want to take a guess on what this is? Well, it is, yeah.
Oh.
It's our planet. So I just wanted to illustrate to you what these maps that you saw previously are. Basically, it's just a projection of the entire sky on a flat surface. So if you look at our Earth, this is what it would look like. Okay. And the reason we have these satellites is because Planck is not the first one to do this. Planck is the 3rd generation one. And so COBE was the 1st generation one, WMAP was the 2nd generation one. And so by going to by different generations of satellites, of course, resulted in due to an improvement in technology, you get sharper and sharper images of the sky. As you can see here, the same sky looked like this with COBE, looked like this with WMAP, looked like this with Planck. And you can see a lot more detail, a lot more structure. It's almost the difference between a bad cell phone camera and a good cell phone camera. And then Planck, of course, not only just had improved spatial resolution, but it also had much, much better sensitivity. And as I said, much better measurements to control what all these different components of emission are doing. So if you put this all together and you study the entire sky, you peel off the layers of the onion, well, what you find is these 5 spots across the sky. So yes, you get all the other radiation, of course, and those who want to study that, that's fine. One person's signal is another person's noise. But there are these 5 regions across the sky, well outside the plane of our Milky Way, and they have unusual properties. And by unusual, I mean they have excess emission at one frequency, at 143 gigahertz. Every other patch of the sky looks reasonable, but these 5, for whatever reason, have excess emission at 143 gigahertz. So that's a frequency, of course, that you can't see with your naked eye. So now those who are used to looking at intensity plots, this is what the spectrum of those 5 regions looks like. This is intensity as a function of frequency in those 5 regions, 1, 2, 3, 4, 5. The points are the measurements. The line is a model, which is what we would expect. And for those who look at noisy data or are used to looking at signal to noise, you can see that each of these points at 143 gigahertz is deviant from the line. And you can say, well, okay, this one is sort of close and this one is maybe, within the noise. And this is the problem, right? This is the problem in studying for these signals. It's right at the limit of detectability, even with the state-of-the-art satellite that we have. The statistical significance is 3 sigma in some cases, it's 5.4 sigma, 5.7 sigma in other cases. And the probability that you would have something which is 3 sigma is pretty high. It should occur in a map every 5 times, but for something to occur 5.7 sigma is impossible. It needs to have a 1 in 70,000 all sky maps. You need 70,000 observations of the sky to get something like that. And of course, we don't have 70,000 observations of the sky. So that is the statistical significance of the excess emission that we're seeing at 143 gigahertz. And it's very hard to explain this. Every other part of the universe looks fine. Every other part of the sky looks fine. But these 5 regions have this. And I would say this region here is the most significant at 5.7. I would say maybe this is consistent with noise and this is consistent with noise, but this one and maybe this one are very hard to explain. And so there's a model which you can try to explain it, which is shown as the dotted line, which now goes through the points. And that explains, that is used to explain why there may be this excess emission because of these collisions with other universes. So let me summarize here. We've gone through our entire universe in 20 minutes or so. And basically the physical conditions, what I've explained to you is our universe is a very large place. We live in an ordinary planet around an ordinary star in an ordinary galaxy. But our universe, to have our universe, it needs initial conditions need to be fine-tuned at the 1 part in 5 to the 10 to the 24. And that either it indicates our universe is special, or it means there are other universes out there where conditions were not optimal for life to form. So this is one of the first pieces of work which attempts to study the existence of these alternate universes. And it ties in with string theory, because string theory predicts that there are 10 to the 500 metastable states of vacuum, of which our universe could be one, right? So there are 10 to the 500 other universes out there. Planck was a satellite launched in 2009 to study the radiation from the formation of the universe, and it provided evidence for some anomalies in certain regions of the sky. It's the first test of the alternate universe hypothesis. And if any of those anomalies with excess emission at 143 gigahertz are statistically significant, they need to be from bubbles. They could be from bubbles with different physical parameters colliding with ours in the early universe. But I must emphasize that current measurements are not conclusive evidence for alternate universes. But the point remains that the origin of these regions in the sky is unclear. Finally, and especially in this, since we live in an age of misinformation, the scientific method is to assess the data critically. You make a hypothesis and a prediction, and you take more data to test the hypothesis. So if nothing else, when somebody tells you something, I urge you to assess whatever data is presented to you critically and ask the right questions to give you a better understanding on why something may be real or not. So I'll stop there and take questions.
Chary, are you able to hear me?
Yes.
Yeah, okay. I always get blown away when we say we are able to send a satellite and map the entire universe. I'm trying to comprehend what would that normal line mean, and why would that anomalies give you a clue of alternate universe or life? What is your fundamental approach to say that there are 5 areas potentially alternate universes? I'm trying to understand. In simple layman terms, I don't understand 99.999% of what you said, but I'm trying to understand what is the basis of which you're trying to make such a hypothesis.
Well, let's look at this. This is a pretty good illustration of the problem, right? So let's look at this image here. Let's zoom in on this. Here, this is an actual image of the sky with the Big Bang radiation. Now you see these regions. These are regions of hot spots and cold spots. And the reason you have hot spots and cold spots is because of quantum fluctuations in the early universe, out of which all galaxies formed out of. But in general, the temperature of any of the brightness, the intensity from any of these cold spots, it's about the same at 143 gigahertz. So we can predict what the properties of this cold spot are by looking at the radiation in the immediate vicinity. What's happening here is some of these cold spots are not cold enough. There is excess emission at 143 gigahertz. And we go through this whole process of why is there in cold spots, why is there excess emission at 143 gigahertz? And it's impossible to explain it by any other means. I mean, you could always say, oh, it's the dust in our galaxy, or it's the dust in our solar system, or dust in our galaxy, or it's because of some other source, or something like that. But none of those hypotheses actually explain why a particular region, which is particularly cold, has excess emission at 143 gigahertz. So for it to be explained by the collision of a universe with other physical properties, that universe needs to have a lot more energy density. It needs to have more energy density than ours, but it had so much energy density that it wasn't able to live for a very long time. It wouldn't live for 13.8 billion years. It would basically collapse on itself within within a fraction of a year. And so, but in the early universe, it's like bubbles in a soda bottle. You don't know, if you were in a bubble, you would not know about the existence of any other bubble unless it collided with ours. And so did one of these high energy density universes collide with ours when our universe was rapidly expanding? And that's what we're seeing as excess emission at 143 gigahertz. That's a hypothesis. Now the next step would be to measure the spectrum of this radiation with greater precision and then see if it really is that or something else.
Dr. Ranga, there's a question about, there's a great presentation. There's a lot of great comments about the people are blown away with your presentation here. It is mind-blowing. But the question is, what is the incentive for the corporations to doing this research? Are they helping you? And is it mainly funded by the universities? And who funds all these activities for alternative universe? So if you can provide some details.
Yeah, corporations don't fund this research. There is no, well, corporations exist to earn profits for their shareholders, and funding astronomy research, which is a pure science, is not entirely profitable, or in fact has no profit whatsoever. So all our funding comes out of science grants. NASA is the biggest one in the US, but the NSF plays a role. So all this work was funded by NASA. And I would say the number of organizations, apart from NASA, which can fund this around the world, are the European Space Agency, the Japanese Space Agency, and to a smaller degree, the Australian Space Agency and the Australian Space Agency. So yeah, all this funding comes out of government agencies whose charter is to push the envelope of knowledge, but corporations don't fund any of it.
So related to that, there's another question about what is US DOE's contribution?
What is whose contribution?
DOE's contributions.
Department of Energy?
Yes. I think that's what Muthu means, right?
Yeah, so the Department of Energy was absolutely crucial for one aspect of the study, which is computation. The Department of Energy runs these supercomputing labs, one of which is up in Berkeley, but there are others across the country. And that computation, those labs were crucial for the supercomputers were crucial for generating multiple maps of the sky. You remember I told you the statistical significance has to be 1 in 70,000 maps or some crazy number. So what the Department of Energy supercomputers did was simulate the sky multiple times, taking different realizations of the noise, which enables us to assess what the statistical significance of any signal is, or if something is really anomalous or not. So that was the big role played by the Department of Energy.
Okay, very good. So I have a question. When I'm on the same slide, you are on slide number 12. When I look at the end of it, you see a lot of variations of the last points are, if I see the line and then I see that is not sometimes, even though the line is kind of going to the upward, the last point is really down. So what is the significance of that?
Yeah, absolutely. But this illustrates the point perfectly. So what is this highest frequency point? The highest frequency point is this map here, okay? And this map is almost entirely dominated by the gas and dust in our galaxy. It overwhelms the noise by a factor of 1,000. So that's the reason why you have this point, which is anomalous from everything else, but it also has a very large uncertainty associated with it.
Yes.
So this is why astronomers, physicists, they care about noise with excruciating level of detail. And the error bar basically takes into account the significance of the deviation. And it's statistically not significant. So the highest frequency point is not significant. I can guarantee you this. In fact, none of these other points is statistically significant, and it's not worth talking about. The only ones which are statistically significant are these 5 points at 143 gigahertz.
So there's another question. The person, Ganraj talks about, I have seen a lot of videos related to mission Apollo 19. Can you tell us a little bit about that? I'm very curious to know about that too. So Apollo 19, I've not heard about it. So,
well, I mean, I think this is just pushing the future of human exploration. I mean, all that is not related to any of what I spoke about, apart from going into space, and that's the manned space flight program. So, I mean, the Apollo program was basically set up to put humans on the moon during the Cold War, space race, and it was extremely successful with that. But then moving forward, there is a lot of talk about, well, should we go back to the moon? Should we go to Mars? What name do we give it? I mean, I don't think Apollo 19 is going to be the standing name. So I think that's just a thing which is made up. It's not a NASA formal name. But the point remains that that's all about human space flight and living on other bodies like the moon or Mars, where the conditions are, quite frankly, extremely inhospitable to living on Earth. This is why we need to take care of our Earth really, really well. I mean, when whoever talks about setting up a base on Mars, they have no idea what they're talking about, because humans will not survive very long. I can guarantee you this. So yeah, so take care of our planet.
So Dr. Ranga, one more question and then hand it over. There are always news about sighting of UFO, etc. How much of that is possible?
So the UFO, as the term means, is unidentified flying object. It could be anything. It could be a balloon that has escaped from a children's party. It could be a drone. It could be a bird. It could be some other flying object. So the term is fine. But the big jump in realization is translating a UFO to aliens visiting us. Frankly, as a scientist, the evidence for that is close to zero. It's always ironic to me that despite all the technology that exists, the best images of the UFOs are extremely grainy things, not really scientifically robust data or robust images. So yeah, I don't think it has anything. It probably is a terrestrial phenomenon. It's probably something which is either in the atmosphere or a plane or something left by somebody with a toy. I don't think it has anything to do with aliens visiting us.
Thank you, Dr. Ranga, for fantastic presentation. I'm a space freak. I think this is not enough. I would like to even listen to you more, but from the time standpoint, we are getting to the end of an hour. So I will pass it on to Anjali, and thanks again for your time. And
Thank you
thanks
very
to
much
all
for
the
having me.
participants.
Pleasure.
Kush. Thank you, Dr. Ranga Chary. It was amazing. It was really enlightening, I would say, because other than stars and galaxy we see here from Earth, there is so much there, and you kind of open our eyes. Let me start with thanking basically ASEAN National Organization, Piyush Malik and Dr. Ram, SoCal chapter, Sri Gavini, and our ASEAN Michigan chapter with Muthu, Lalita, Vatsala, and all amazing people of our team. It's really enlightening to really hear about it because I saw your slide about that dense house dense the universe is. It made me like it's our fate to be like exist with that exact perfect density number. Otherwise, this universe won't exist. And for us to be here, that number was so perfect. I don't know where this perfection comes from, universe, but it's just very good to see all these numbers and data that you presented. It kind of really uh, gave us a lot of knowledge. So thank you very much for your time. Really appreciate it. And on behalf of, again, ACI Michigan chapter and all over ASEAN organization. Thank you very much. Appreciate it.
Thanks very much. That's
Yeah.
very kind.
And stay on because we are going to have an open networking session now.
Yeah, and thank you, Dr. Chary. I know we had there were more and more questions coming up as we're concluding your speech. So what we suggest is we have another 20 minutes or so. Anybody that want to ask a question, I saw some questions coming from Umu Gupta and our own Kumar here. So please unmute. Maybe raise your hand, unmute. If possible, come on the video and ask your question.
Yeah, come on screen. I'm sure I can see Sharon. I'm sure Devesh is there. So plenty of good questions. I would.
Yeah, this is Kumu Gupta from Boston. So many years ago, a colleague of mine told me that his brother was enrolled with a program called SETI, and SETI is something that is part of NASA, and they're the ones who keep track of the UFOs, which is about terrestrial lives. And I believe that they have some of these beings stored in nitrogen, to preserve them, and that they're studying them. So do you have any evidence of that?
Yeah, I was just responding to your question about this. So SETI as a program, great program. If you don't look for something, you'll never find it. So if you really want to find, in 1995, there was no existence for other planets around other stars. So the process of taking data and doing the measurements resulted in finding planets around other stars. So similarly, if you want to find evidence for microbial life on other planets, you need to take measurements. SETI is one step above that, which is it's trying to look for intelligent civilizations around other planets by looking for radio emission. So yes, this has been around for a long time in different flavors. I should point out to you that one of the first signals detected was in the 1960s, I believe. There was something which was pulsing at exactly the right frequency over and over and over again. And they called it LGM-1, which means Little Green Men 1. Of course, it turned out that it was a spinning neutron star, which forms from the collapse of a massive star. So yeah, like I said, SETI, you need a program to look for something, because if you don't look for something, you'll never find it. But is that evidence for is there evidence for alien life in any of the data taken? No. And the reason is there's a very high statistical bar. I keep emphasizing this point over and over again. It's not like you see some blip somewhere and you say, oh, that's alien life. That just does not work. That's not how the scientific method works. So none of the signals that have been found so far are evidence for either UFOs or evidence for alien life. So yeah, but the program as it is not funded by NASA. It's actually mostly funded by private individuals, private wealthy individuals who are interested in this kind of stuff. And that's partly because it's a zero-sum game. NASA has a finite amount of funding. Are you going to put a large amount of funding for the search for a wild goose chase on the search for whatever alien life or whatever? Are you going to put those finite resources into something which may have a more immediate impact on a short horizon, 1 to 5 years? And so, yeah, I think that's the main reason why it's not funded by NASA and mostly funded by private donors. Does that answer your question?
I think
Yeah, I guess yes and no. That's fine. That's fine.
Okay.
So Dr. Ranga, this is Muthu. I know you mentioned about this earlier too. First of all, take care of the planet, which is, I guess, in all of our minds, right, from corporates to research labs and so on. So through these research, do we get any, I would say, side benefit of how to be more sustainable, how to take care of our planet more? Are we finding any kind of new sources of energy or materials, something in those lines that will also help our own Earth's own problem, in the next 20 years, 30 years, the next century?
Earth's problems are not, in my opinion, Earth's problems are mostly human-created problems. We know how to solve these problems. We know between solar and wind, and we can pretty much solve 90% of the carbon emissions problems. It's just that humans are unwilling to take the initiative, or there's inertia in the system to try to solve those problems. Yes, there is a small fraction who try to do it, but the vast majority are totally indifferent to the problem because it doesn't affect them on the time scale of a decade or two. So yeah, I don't think we need to go out into space to try and solve this problem. I think the problems are eminently solvable right now with current technology. I think the one thing which is going to be a problem is carbon capture. And I don't see any evidence that carbon capture right now can be scaled up at the level at which is needed to basically mitigate the global climate change, global warming problem. Yeah, so, but we can cut off emissions. Honestly, we can cut off, if every household had solar panels and tapped into wind energy, we'd basically cut down emissions by a dramatic amount, and that would solve the problem.
Thank you. The solution is within us, I guess.
Yeah.
So, Dr. Ranga, I wanted to get your perspective about the James Webb, the new telescope, and what is its capabilities, because it also seems like from Hubble to now, the technology and our ability to see has gone drastically. And where do you see the future of the space telescopes and our ability to see alternative universe standpoint?
Well, so yeah, so there is no mission right now to study alternate universes. I can assure you of that. So right now, the best hope is, well, somewhere 20 years down the line or 30 years down the line, we may have another mission which will study this. But right now, we don't have anything of the quality of Planck with more frequencies. There is a Japanese mission called LightBird, but the reason LightBird is not that good is because it's targeted for a slightly different thing. LightBird is to study the gravitational waves, which are supposed to prove the existence of the rapid expansion of the universe. So James Webb is not going to make any dent on this topic. It'll study other things, yeah, I mean, there are missions which are being imagined to do other things, like study properties of exoplanets or study the properties of X-ray gas in massive clusters. But there isn't any evidence that there isn't any plan to, at least on the timescale of the next decade, to launch a mission to study study alternate universes.
So I think there's one question here. There's millions of different energies with a huge amount above the Earth. Humans are finding, discovered that, analyze them, but can human make some control over it? So we have all these energies, and do we really have a control over what kind of energy is out there? And
no, I mean,
I think
the
that's-
energy density, yeah, it's not just energy, right? It's energy density. The only thing which has high energy density is the sun. It has a very high energy density at the top of the atmosphere, and then only 1/3 of it makes it all the way, through to the bottom of the atmosphere where we are. So yeah, I mean, you can control it between the top of the atmosphere and the bottom of the atmosphere, but tapping into something like the vacuum energy density is so low compared to the energy density from the sun that it doesn't really matter. So yeah, it's not just energy, it's energy density. So energy per cubic centimeter.
Oh, that's a very good point. Good. Thank you.
So I have one question, please. Can you hear me?
Yeah.
Okay. So this is, I've been thinking about this some time back, and I could never wrap my head around this. All this mass that we know, I mean, the entire universe mass as we know it, right? The 10 power 24 or whatever you mentioned, that is at the point of T0 at the Big Bang time, they're all concentrated into that point.
It's not mass, it's energy, by the way. It's energy,
okay.
energy density.
At that point. Okay, energy. So, but in the, I mean, at some, so much energy and mass are equivalent, right? In some sense. So at that point, it's very hard for me. So if the conservation of mass or conservation of energy is held at that point, such a unimaginable energy or mass being concentrated at one point, some very hard. Is that how I should think about it? That really all that energy and mass was really concentrated, or did we come across this energy and mass violating conservation principles later on? And okay.
So yeah, we didn't. It's absolutely right. It's all conserved. So it's just that the universe has expanded so much since then that the energy density and the mass density has gone down, and this is why. So I mean, as I said, it's expanded by a colossal amount since back then, when everything was compressed into a really tiny region. And so what has happened is the matter density. So as the universe expanded, it cooled. It was more than 1 billion degrees. The average temperature of the universe in that early universe was more than 1 billion degrees. What it is right now is 3 degrees Kelvin. So essentially, the universe has expanded by that much that it has cooled. And because it has expanded that much, the density has gone down by a very large amount. And so the average energy density or matter density out there is very, very small. It's basically 1 hydrogen atom per cubic centimeter.
Okay. I have a very different question. I'm sorry, I'm taking up all the time here. One more question, please. I also, regarding all the harm that we are doing to our universe, right? One of the things I hear about is how we are, by doing all these emissions, we are doing something that might cause sun's sun's rays, the bad rays from the sun to penetrate the earth, which has been shielded before. And is how likely this? Can you speak about that, basically?
Well, the Earth's atmosphere basically protects us from the sun and all the charged particles which are impacting the top of the atmosphere. So yes, if, as you know, back in the 70s, there was a problem with the ozone hole, right? So the ozone essentially blocks all the ultraviolet light coming from the sun. And if there was not ozone, and there's the ozone hole, which was caused by chlorofluorocarbon refrigerants, CFCs. If that hole had become larger, well, the people who live close to those holes, essentially our Australian and New Zealand colleagues and up in the Arctic Circle, they would have a higher incidence rate of skin cancer because the UV radiation is no longer blocked by the ozone. So yes, if we destroy the ozone, we will have very serious consequences for humans on Earth. But fortunately, the CFC use has been more or less eliminated, except for some rogue places. But yeah, so that progress has been made on that front. In terms of whether the gamma rays from the sun will ever destroy humankind, not really, because the Earth's atmosphere, well, yes, if we destroy our atmosphere, absolutely, the gamma rays will fry us. But yeah, for as long as there is an atmosphere, most gamma rays from the sun get blocked out. And so most gamma ray observatories are up in space. There are some gamma ray observatories down on Earth. There's one in Namibia, there's one down in Chile, but those detect extremely high energy gamma rays, which are extremely rare. And so they do not have any impact on humankind.
Thank you.
Dr. Chary, I have
hi, I had a question. Okay, go ahead. I'll ask after you.
So I had this question for many years when I was a kid. So is our universe still expanding? So you mentioned
Yes.
regarding the 3 Kelvin. So is it still expanding? And our Earth orbit, so that's good. So it's expanding. And our Earth's orbit, which is elliptical, we say, is it also stretching on the endpoints because of that? We are seeing some temperature changes.
Yeah, so it boils down to the energy density argument. In the Earth sphere, in the Earth-Sun sphere of influence, the biggest, highest energy density is from the gravitational force of the sun. The next biggest is gravitational force of Jupiter. So the expansion, which is because of vacuum energy, is subdominant to the energy density in our solar system. So no, it's not affecting the orbit of our Earth, but the gravitational force of the sun is, because the gravitational force of the sun is the much more dominant force. It's always energy density. Whatever you think about, the argument is always, is the energy density of A greater than the energy density of B? If it's A is greater, then A wins out. Yeah.
Okay, thank you.
Yeah, hi, this is double. Hello.
Yeah.
Yes, this is a double here. I missed the first half today, but if you covered it, then just say that. But we talk about this ever expanding universe. What is it expanding into? What is beyond the universe?
Yeah, the way to think about this is it doesn't. It's like the surface of the balloon. Okay, so humans are intrinsically used to thinking in 3 dimensionals, X, Y, and Z. So but imagine that we were 2-dimensional and we lived on the surface of a balloon. Then the only place we can see is on the surface of the balloon. So you draw any circle from any line from point A to point B on the balloon, it eventually ends up on the balloon itself. What is outside the balloon doesn't even exist. That's the thing. And so that's the difference between 2D and 3D is the best analogy I can tell you. But going from the 3D of our universe to anything else, there isn't anything else out there. So it's not expanding into something. And I know that's a very hard concept to grasp, but that's because we as humans are so used to 3-dimensional space that thinking about something beyond 3-dimensional space, it just doesn't exist. I mean, yes, there is all this talk about n-dimensional space, which may have existed in the early universe, and some of that resulted in contractions and phase transitions in the early universe. But yeah, again, we have not found any evidence for that, so can't venture a guess in there.
Okay, thank you. So then, what does expanding mean?
Expanding is exactly like the surface of a balloon. It's like you're blowing into the balloon, and the surface, the distances between any 2 galaxies in the universe, or most 2 galaxies in the universe, is increasing with time.
Okay,
yeah,
it.
Except, so as we just discussed, except in our solar system or in gravitationally dense places where the energy density of gravity wins out.
Okay, and there's no compensating reduction of distance anywhere else in the universe, which compensates for the fact that it's increasing somewhere.
That's right. No, there isn't. The only reduction in distance is happening in places where the gravity is the dominant force and galaxies are merging with each other.
Okay, thank you.
So Dr. Chary, we also love to understand the journey of scientists and the technologies that come onto our program. So to inspire the younger generation, could you throw some light, spend a few minutes on what is your journey that took you from engineering college in India to one of the leading scientists in one of these advanced programs here in the US? And can you talk a little bit about that?
Yeah. So I did my schooling in Delhi, and then I was an undergrad in RDC Trichy, which is now called the National Institute of Technology, in computer science. But I think the thing which guided me in astronomy was summer research program. So for all kids, the best thing to figure out whether you get really excited by a field is to spend your summers or winters going to an institution and working on a research topic. The most important skill that you can have is programming. So if a kid has programming skills and some basic physics knowledge, you can go basically do a summer research program. And then you'll see if that's the kind of thing that interests you. Because the one thing about astronomy is it's a small field. There are about 10,000 astronomers, let's say, around the entire world. And it's also a very, yes, there are these large collaborations like Planck, but most of the time is not spent talking to each other or even taking data at the telescope. That's a very small part of it. Much of the time is in writing code and solving equations. And then you'll see if that's the kind of thing that gets you jazzed. And personally, it got me jazzed. And when I was a summer undergraduate researcher, and this was back in the Raman Research Institute and Tata Institute of Fundamental Research. And so that's what got me to move from computer science to astronomy. And once you do that, then you can enter graduate school because you have some research experience, and you know that that's the thing which gets excites you. And honestly, you shouldn't get into a field unless you're excited about it. This is the one thing I can emphasize, because it's as what's the old saying that research is 99% perspiration and 1% inspiration. And I think that's 100%. That's pretty much true in our business. You have a great idea, and that's a very small part of it. The rest of the time goes into analyzing the data, writing equations, or solving the problem.
Great, thank you.
But I guess when you get into a field, it's 100% inspiration and 0% perspiration. Then it's followed up.
Yeah.
Muthu,
Yes.
do you want anybody else to just come up
Yeah,
and say?
Muthu,
If
I'm
anybody
going
else
to
has
sign
any
off now.
questions.
Muthu, I'm going to sign off now. So because I have to take care of something else.
Sure.
Okay.
But
Yeah,
it's
Thank you
very
very
nice
much.
to meet all of you. And
thank you so much for your time. Really appreciate like this unfathomable data that we would never get a chance to even look at and understand. So it's really kind of you to join us and inspire us and the younger generation especially. And also I'd like to make a special shout out to Ram, who couldn't join today. He was kind of one inspiration, one bridge to get us connected with you. So thank you, Ram.
And he did join. I think he did join for a very brief moment. Yeah.
Okay.
Yeah, drop me an email if anybody has any questions. My email can be easily found on the web. So yeah, take care, everyone.
Thank you very much. Thanks. Bye.
Thank you.
Pleasure.
Thank you.
Bye-bye.
Bye.
Thank you.
Thank you very much.
Do we open up for networking? Or?
Yeah. If we have 15 minutes, if our local members and people want to just stay on and network, we have 15 minutes. Feel free. Don't be shy. Turn on your video, then we can have a chat.
Yeah.
So
We should stop the live. We should stop the live.
Go ahead.
Sorry, just one thing I wanted to say. Vale, I need your picture. It was too tough to find it on the internet.
He's
Go
a
ahead.
social media shy person, probably.
Okay, I had a follow-up question, but he's gone, but maybe one of you